Lesson: Smart contracts, design challenges and failures. Smart contracts represent a revolutionary step in the evolution of blockchain technology, promising to automate and streamline contractual processes with unprecedented efficiency and transparency. However, the promise of smart contracts is often tempered by significant design challenges and a history of notable failures. Understanding these challenges and learning from past failures are crucial for professionals seeking to mitigate risks associated with smart contract deployment and management. Designing smart contracts involves translating legal and business agreements into code that is executed on a blockchain platform. This translation is fraught with complexities due to the inherent differences between legal language, which is often ambiguous and open to interpretation, and programming languages, which require precision and specificity. The challenge lies in ensuring that the coded instructions accurately reflect the intent of all parties involved and that they perform as expected under all possible scenarios. One of the primary design challenges is ensuring the security of smart contracts. Vulnerabilities in smart contracts can be exploited by malicious actors, leading to significant financial losses. The infamous DAO hack of 2016 serves as a stark reminder of the potential pitfalls. The DAO, a venture capital fund operating through smart contracts on the Ethereum blockchain, was hacked due to a recursive call vulnerability, resulting in a loss of approximately $60 million worth of Ether. This incident underscores the necessity for rigorous security audits and testing before deployment. Tools such as MythX and Oyent are invaluable for automatically detecting common security vulnerabilities in Ethereum smart contracts. These tools analyze code for bugs and vulnerabilities, enabling developers to rectify issues before contracts go live. In addition to security concerns, smart contract design must also address issues of scalability and performance. As blockchain networks like Ethereum become more congested, the execution of smart contracts can slow down, leading to higher transaction fees and delays. This scalability challenge necessitates innovative solutions, such as the implementation of Layer 2 protocols, which process transactions off the main blockchain to reduce congestion and improve efficiency. Additionally, frameworks like the Raiden network for Ethereum offer practical tools to enhance scalability by enabling faster and cheaper transactions through off-chain processing. Another significant challenge is ensuring the interoperability of smart contracts across different blockchain platforms. As the blockchain ecosystem evolves, various platforms emerge, each with unique features and capabilities. Ensuring that smart contracts can operate seamlessly across these platforms is critical for maximizing their utility and adoption. Projects like Polkadot and Cosmos are at the forefront of developing protocols that facilitate interoperability, allowing smart contracts to interact with multiple blockchains without compromising security or performance. The legal and regulatory landscape presents additional hurdles for smart contract design. Since smart contracts operate in a decentralized and often anonymous environment, determining jurisdiction and legal enforceability can be complex. Moreover, the immutability of blockchain, while a core feature, poses challenges for compliance with regulations that require the ability to amend or delete data, such as the European Union's General Data Protection Regulation. Legal frameworks and guidelines, like those proposed by the International Swaps and Derivatives Association, aim to bridge the gap between traditional legal contracts and smart contracts, providing standardized templates and protocols to ensure compliance and enforceability. To address these challenges, professionals can adopt a structured approach to smart contract design and deployment. The use of frameworks such as the Smart Contract Development and Deployment Framework can guide the process, ensuring comprehensive risk assessment and management. This framework emphasizes a step-by-step methodology, beginning with the identification of business requirements and objectives, followed by the design and coding of the contract, rigorous testing and auditing, and finally deployment and monitoring. Case studies of smart contract failures provide invaluable lessons for practitioners. For instance, the Parity Wallet hack of 2017, which resulted in the freezing of over $150 million worth of Ether, highlights the risks associated with library contract vulnerabilities. In this case, a vulnerability in the parity multi-signature wallet library allowed an attacker to gain ownership of the wallet contract and subsequently lock users' funds. This incident underscores the importance of thorough code review and the adoption of best practices in smart contract development, such as minimizing code complexity and avoiding reliance on external libraries without proper vetting. In addition to learning from past failures, smart contract developers can leverage tools and platforms designed to enhance security and reliability. For example, formal verification, a process that mathematically proves the correctness of code, can be employed to ensure that smart contracts behave as intended. Platforms like Certic provide formal verification services, allowing developers to identify and rectify potential vulnerabilities before deployment. Statistics on smart contract vulnerabilities further highlight the need for robust design and testing practices. A 2019 study by Consensus Diligence found that of the roughly 1 million smart contracts analyzed, about 3% contained critical vulnerabilities that could be exploited. This statistic underscores the prevalence of security flaws in smart contracts and the necessity for comprehensive testing and auditing. To mitigate the risks associated with smart contract failures, professionals should adopt a multifaceted approach that incorporates best practices from software engineering, cybersecurity, and legal compliance. This includes regular code audits, the use of automated testing tools, and collaboration with legal experts to ensure regulatory compliance. Additionally, ongoing education and training in the latest technologies and methodologies are essential for maintaining proficiency and staying abreast of emerging threats and opportunities in the blockchain space. In conclusion, while smart contracts offer significant advantages in terms of efficiency and transparency, they are not without their challenges. By understanding the design challenges and learning from past failures, professionals can implement effective strategies to mitigate risks and enhance the reliability and security of smart contracts. Through the adoption of practical tools and frameworks, as well as continuous learning and adaptation, the potential of smart contracts can be fully realized, paving the way for their broader adoption in various industries.